Hi, and welcome to our lesson 6-7. Today we're going to be talking about the dot product, which is a measurement that works with vectors, two vectors. However, when we did other arithmetic with vectors, adding and multiplication, etc., we added two vectors and got a vector. The dot product doesn't work that way. The dot product of two vectors results in a real number, and that number can tell you some information about the vector. So that's our introduction. We're going to suppose that we're starting with one vector, and you can see it here, and a second vector. The dot product, by definition, would be shown this way. It looks like multiply, but really it means dot, right? Vector 1 dot vector 2, or dotted with vector 2. And the arithmetic that you do to come up with that real number is this. You multiply a1 times a2, so you multiply the two horizontal parts together, and then you add to that the product of the b parts, the vertical parts, so b1 times b2. So in words, the dot product of two vectors is the sum of the products, so you're adding the products of their horizontal components and their vertical components. And we've got just a tiny little couple of practice problems here for you to try finding that dot product. So we have vector 1, or just v, the vector v, is 7i minus 4j, and vector w is 2i minus j. We're going to find the dot product v dotted with w. So if we think about this as being a and b, we're going to multiply the a's. So 7 times 2. And we're going to add to that the product of the b's, so negative 4 times negative 1. You do a little arithmetic there. That's 14, and it's going to be plus a positive 4 since you multiplied the two negatives. So the dot product of v and w is 18, right? It just produces a real number. It's kind of interesting, a little interesting, to think about a vector dotted with itself. So this is saying do w dotted with w. And that means that we're going to multiply the two a's, which would be 2 times 2, and the two b's, which would be negative 1 times negative 1. We're going to add those results together. That's a 4 plus 1, or 5. And the reason I say this is interesting, folks, is because this actually, it's the square of the magnitude of that vector. If you think about that, square of the magnitude of that vector w, because to find the magnitude, you'd square and add and then take the square root. Okay? So it's another way of getting at the magnitude for a vector. We also want to look at how we can use the law of cosines to derive another product, or another formula for the dot product of two vectors. This is easy. If all we're asked to do is find the dot product and we're given two vectors, this is what I'm going to do every time. But if we really want to use the dot product to help us solve problems, then there is another formula that will maybe be more convenient for that kind of problem solving. So, okay. What we're going to do is take you through a derivation of a formula. And I'll tell you what, one thing, when you derive a formula, you only have to do it once. And once we're finished, we'll know that this formula will always work to replace the dot product, or it will allow us to find the dot product. Alright, so you can see we have two vectors v and w here, and the points at their ends are shown, a1, b1, a2, b2. And vector u completes a triangle with these two vectors. And of course you can see that the ends of vector 2 are also those coordinates. So what I'm going to ask you to do is think about, we're going to find the magnitudes of all three vectors, and then we're going to use them along with the law of cosines, and we'll see how we can relate this angle to this length. Alright, so if we're going to find the magnitude of vector v, we think to ourselves, well, vector v goes between 0, 0 and a1, b1. So to find the magnitude of this piece, we can use the distance formula. So we start out with the big square root, and then it will be the end point of this, so the terminal point, a1 minus 0. Well, I'm not going to write minus 0, but I will write a1 squared, because that's the horizontal component of that vector, and then plus b1 minus 0, but I'm not going to write that, squared. And there we have the magnitude of that vector v. Using a similar argument, the magnitude of vector w will be the square root of a2 squared plus b2 squared. And then we get to this guy, the vector u. And what I would love to have you think about is this. So the way that this is pictured, a1, b1 is the terminal point in this vector. So if we were going to find the magnitude for that one, we would think a1 minus a2 squared plus, and now we do the vertical distance, b1 minus b2 squared. And that looks ugly, but it's just the distance formula for this line. All right, now it says that we want to write a law of cosines equation that relates our vector's magnitude and this angle. So I would love to have you think about that. Our vector's magnitude is just the length u, or u squared, or we could write it this way. The magnitude of u squared has to equal, and the law of cosine says you sum the other two sides and add them, and then you take off that correction factor, since we're not in a right triangle, so it's minus 2 times magnitude of v times magnitude of w times the cosine of theta. Law of cosines relates an angle and the side opposite. Well, we have expressions for a lot of this stuff, so let's put those in there. The magnitude of u is this. If we square it, we just lose the radical. So I hope that you're going to follow that. We're squaring the magnitude of u, so what we get out of that would be this. a1 minus a2 squared plus b1 minus b2 squared. That has to equal, according to this, the magnitude of v, which is this, but squared. And so if we square the magnitude of v, we lose the radical. It's a1 squared plus b1 squared plus the magnitude of w squared. Well, that's going to be a2 squared plus b2 squared. And then it's this, minus 2, and I'm going to leave these alone. Magnitude of v, magnitude of w, times the cosine of our angle theta. That doesn't look a whole lot better right now, but we're going to make it look good. We're going to square this parenthesis, and for those of us who are FOILers, I want to write it out that way. We're multiplying like this. a1 squared, a sub 1 squared, then we have a minus a1 a2 and another minus a1 a2, so that's minus 2 a1 a2's, and then the last that gets us a positive a2 squared, so plus a sub 2 squared. We're going to use the same logic on this one, so, and it was an addition, this is a plus sign, so now we're going to have b1 squared minus 2 b1 b2, and then it'll be plus b2 squared, and all of that equals this, a1 squared plus b1 squared plus a2 squared plus b2 squared, and then minus 2, and it's the magnitudes of the two vectors v and w multiplied by the cosine of theta. Now, you may be thinking, holy moly, Mrs. Brownfield, that looks awful, but look at this. There's an a1 squared on both sides, so those are going to subtract off. There's an a2 squared on both sides. That's going to subtract off. A b1 squared, that subtracts off. a b2 squared, and that subtract. If you collect what's left, we're looking at minus 2 a1 a2 minus 2 b1 b2 equals, and then we have this negative 2 magnitude of v magnitude of w cosine theta. Now I'm just going to do a little algebra, divide everywhere by negative 2. This is all hooked together, and these two terms both can be divided by negative 2. So that's going to leave us with this, a1, a2, plus, because we're dividing by negative 2, so it changes it to a plus, b1, b2 equals magnitude v, magnitude w, cosine theta. And ladies and gentlemen, I would present to you that that right there, a1, a2 plus b1, b2, that is the dot product. It should look familiar to us. That's the same formula we had just a moment ago. And this says that that is equal to, we have an alternate formula for that dot product, folks. It's the same thing as the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle that's in between them. This formula is useful also because you can use it to find theta if you have to. Okay, if you have two vectors, you can find the angle in between them using this formula, and that's kind of nice. All right, let's put this to work a little bit. Orthogonal vectors are vectors which meet at right angles or are perpendicular. Right? They meet at right angles or they are perpendicular. If two vectors are orthogonal, then the dot product, using that new formula that we just came up with, if the angle between them is 90, this will equal 90, folks, and that's because the cosine at 90 degrees is 0. So you can say that two vectors are orthogonal if and only if their dot product is equal to 0. Let's see if we can decide whether or not we have perpendicular vectors here. Here's our first vector, it has an A and a B. Here's our second, it has an A and a B. And what we need to do is find their dot product. We do not have to go fancy and find their magnitudes because we don't know what the angle is. So this new formula won't help us, but the old one will, the one that's easier to use. And that is A1, A2 plus B1, B2 is their dot product. In this case, that would be a 2 times a 6 plus a 3 times a negative 4, and that would give us 12 plus negative 12, which is 0. Dot, dot, dot. These vectors are orthogonal or perpendicular. So if we have to find out about whether or not they are perpendicular, using the dot product with the vectors is wonderful. But we want to show you just an application where the dot product will be helpful to you. And that is in determining the amount of work that's being applied in any specific situation. What it says here, and I know you can read, you don't need me to read it to you, but if a constant force F is applied to an object, moving it from point A to B in the direction of the force, okay? I want to have you think about this. I have a picture of a guy pushing a car out of gas, probably. The force that he is applying, he's pushing directly ahead, the car is moving directly ahead. That force is being applied along the line of motion. I want to write that here. This is along the line of motion. He's pushing in the same direction that that car is moving, along the line of motion. If that's the case, folks, then the amount of work that's being done is the magnitude of the force times the length of the segment AB. Okay? Okay, it's the magnitude of the force times the length of AB. And remember, when we put no bar across it, that means length. And if you wanted that in words, it's the magnitude times the length. Okay. That's if the force is being applied in the same direction as the object is moving. A lot of times, though, that's not what happens. This man who's pulling the wagon, for instance, the force that he's applying to the handle of this wagon, he's pulling upward, right? It's on an angle. The wagon, however, is moving on the horizontal, so the force is not being applied along the line of motion. In this case, and I'm going to just draw arrows here, he's pulling up while the wagon's going forward. Okay? In that case, the dot product can help you determine the amount of work done by the force. And the amount of work is W. You can find that by doing the force vector dotted with the length vector. The force vector dotted with the length vector. All right. It is, in this case, easier to use the alternate formula for the dot product, and I could show it to you. I would love, if you are interested, okay, I'll put this out there. If you're interested, I will show you tomorrow how you can do this problem using the other dot product formula, right? Because we know that you can split the vectors up into their horizontal and vertical components, and we could do it that way. However, this problem is much easier to solve if you use that alternate formula for the dot product. So what we're going to think is the work that's applied will equal, and it is the magnitude of the force times the magnitude of the length vector, or its length, okay, times the cosine of the angle between them, cosine theta. That's the formula that we're going to use. Suppose it says a child's pulling a wagon along level ground by exerting a force of, okay, here we go, 20 pounds on a handle that makes an angle of 30 degrees with the horizontal. So as the force is being applied to the handle, it says 20 pounds, and it makes an angle of 30 degrees with the horizontal. So here's the ground, and that's 30 degrees, and he's pulling a wagon in that direction, okay? And it says, let's see, how much work is done by pulling 150 feet. So this is 150 feet. This is the 20 pounds of force, so I should put a label on there. According to the formula for work, if we take the magnitude of the force vector, that's that 20 pounds that they told us about, the length that he's pulling, right, that's the distance vector, if you will, 150 feet, times the angle in between them, or times the cosine of the angle in between them, we can find how much work is being done to pull that wagon that far. Let's get my calculator out here for a second, and we want 20 times 150 times the cosine of 30 the amount of work that's being done is 2,598.1 it was about, and these would be foot-pounds. That's the label that goes with it. I would love to show you the geometric way of solving this. If you ask me about that tomorrow, we'll talk about it for sure. But for now, we'll ask you to go to the U-Try and do that at your earliest convenience. Bye-bye.